So in this video, I'm going to start talking about complex numbers, part of my complex variable discussions. So complex numbers take the form, of course, a plus bi, where a and b are real numbers, right? So what's interesting is that the complex number, which we denote as I, another notation for it is J, but J is used by electrical engineers because I is reserved for current. That's sort of just interesting trivia. But, I equals the square root of -1, which is interesting because this comes up from trying to understand the solution to this polynomial, x squared plus 1 equals 0. If you look at this, obviously x squared equals -1, so x equals square root of -1 plus minus. So, and of course, obviously, you can say that, I squared is equal to -1. So another identity is you can say that I equals -1 over I, which is a very interesting and helpful identity. So really, when we look at complex numbers, we think of them as having two parts, a real part and an imaginary part. So if we say that, for example, z, which we use to denote complex numbers generally, z equals a plus bi. So notationally, we'll say that the real part of z is equal to a, and the imaginary part of z equals b. So this is just a notational thing. It's basically how you talk about complex numbers. So if we want to think about complex numbers geometrically, if we make a little plot here, like so, and we have a complex number, and we're going to say this is z. So it's going to have a real part, and it's going to have an imaginary part, which we denote the complex numbers like this. So we can think about this thing like a vector, right? There's a theta here. So we can think about the fact that z can be written as, right, this would be the x part, and this would be sort of the y part if we want to think of classical geometry. So z equals cosine theta plus I sine theta, because this right here are the complex numbers, and this here are the real numbers. So what's sort of interesting to think about this is that, geometrically we can say some things about this from this picture. So we can say that, the magnitude of z, the length of it, is equal to, if we denote a complex number as z equals a plus bi, then from the Pythagorean theorem we can say that the magnitude of z, because right we have a right triangle right here, is equal to a squared plus b squared. So another interesting thing is that we can say that theta is equal to the inverse of b over a, which is another geometric argument based on this guy. So what I want to end on is sort of a very key way to specifically represent this guy. So what's really interesting about this guy is that there's a relationship here between this and exponentials that we call complex exponentials. And it really helps when you're doing operations with complex numbers. So if we have z equals cosine theta, you know, right? We can represent almost all complex numbers here. These are special complex numbers, right? Because if I look at the magnitude of this guy, hold on. If I look at the magnitude of this guy, then that's equal to the square root of cosine theta squared plus sine theta squared, which we know from identity that this is just equal to the square root of 1, which is just equal to 1. So this is the set of complex numbers that have magnitude 1. So if we think about on the complex plane, we have a unit circle on here with radius 1. And this is basically all the complex numbers that exist on the outskirt of this circle. Not on the inside or the outside, just the ones that have magnitude 1. So if you wanted a more arbitrary circle with arbitrary radius, then you can basically write z equals some radius, the radius you want, times cosine theta plus I sine theta. So with this, you'll basically get families of complex numbers that will exist in some circle with radius r. So let me get to an important identity. So if we look at z equals cosine theta plus I sine theta, we can basically say this is equal to a complex exponential. And I won't prove this, but it's a very interesting proof to say that this is, well, I'll do that in another video. I'll prove why this is true. You can use power series. But so what's interesting about this is that this right here is equivalent to this. And that's going to be very helpful for doing operations. Like you can think about operations between complex numbers, adding them, dividing them, and multiplying them. If you have them in this form, it's good. So what's interesting is you can represent any complex number in this form. And the most general way you can think about it is you can represent any complex number as r. Hold on. So if we have a complex, if we have a complex number, if we have a complex number being equal to a plus bi, then we can represent any complex number as being re to the I theta, which are the radius that equals the square root of a squared plus b squared, and theta, as seen below, is equal to the inverse of b over a. So you can basically represent any complex number as this. And that's very helpful, especially when we're doing operations in the future. So I think in the next video I'll actually prove, there's multiple proofs for this, but I'll give a power series proof of why these are equal. So until next time, see you later.